Welcome to AI Frontiers, where today we explore the cutting edge of robotics research through a collection of 17 papers published in May 2025. These papers represent the forefront of innovation in the computer science subcategory of robotics, known as CS.RO in the arXiv preprint server classification system. In this episode, we'll delve into the latest advancements, methodologies, and groundbreaking results that are shaping the future of robotics. From autonomous driving to dexterous manipulation, these papers showcase how researchers are pushing boundaries to create increasingly capable robotic systems that can interact with our physical world in sophisticated ways. Robotics in 2025 stands at the fascinating intersection of mechanical engineering, computer science, and artificial intelligence. This multidisciplinary field focuses on creating systems that can perceive, reason about, and physically interact with the real world. Current research priorities center around three main areas: autonomous driving, where vehicles must navigate complex environments safely; dexterous manipulation, enabling robots to handle objects with human-like skill; and human-robot interaction, facilitating natural collaboration between people and machines. Modern robotics research leverages powerful techniques, including reinforcement learning algorithms that improve through trial and error, large language models that enhance reasoning capabilities, and predictive control systems that optimize future actions. What makes current robotics research particularly noteworthy is its focus on addressing real-world challenges in perception, manipulation, and adaptation to changing environments. Today's robots are increasingly moving beyond structured factory settings to operate in unpredictable human-centric spaces, requiring more sophisticated intelligence and adaptability than ever before. Our first major research theme focuses on autonomous driving and navigation systems. Several papers present significant advancements in this domain. Liu and colleagues introduced DSDrive, a unified reasoning planning framework that incorporates compact large language models. This approach integrates sophisticated reasoning capabilities while maintaining computational efficiency, crucial for deployment in actual vehicles. Similarly, xDriver, also by Liu and collaborators, presents a multimodal large language model framework that leverages chain-of-thought reasoning to enhance both perception and decision-making in autonomous vehicles. This approach improves not only performance, but also the interpretability of driving decisions. Sermon and colleagues address the challenge of personalization with their multi-objective reinforcement learning system for adaptive autonomous driving. Their approach enables vehicles to adapt to individual driver preferences without requiring policy retraining, a critical factor for user acceptance. Another innovative approach comes from Atsuda and colleagues, who propose a collaboration between large vision language models and model predictive control to deliver both task scalability and safety. Across these papers, we see a consistent focus on balancing sophisticated reasoning capabilities with the computational constraints of real-world autonomous systems. The second major research theme centers on robotic manipulation and dexterity, enabling robots to handle objects with greater skill and precision. Li and colleagues introduced SYMDEX, a reinforcement learning framework for ambidextrous bimanual manipulation that leverages a robot's inherent bilateral symmetry. This innovative approach decomposes complex tasks where two hands must coordinate and exploits morphological symmetry via equivariant neural networks to make learning more efficient. Zhang and collaborators present a novel integrated framework for contact-rich in-hand manipulation, combining contact-implicit model predictive control with tactile feedback-based tracking. Their system allows robots to manipulate objects within their grasp with greater precision and reliability. Liu and colleagues address the challenge of data scarcity with DCODA, a diffusion model for coordinated dual-arm data augmentation. Their method synthesizes novel, viewpoint-consistent wrist camera images for both arms while simultaneously generating joint space action labels, Across these papers, we observe a trend toward decomposing complex manipulation tasks into manageable subtasks and exploiting physical structure as an inductive bias in learning algorithms, approaches that significantly improve sample efficiency and task performance. Our third research theme explores learning from demonstration and imitation learning, which promises to make robot programming more accessible to non-experts. Liang and colleagues introduce CLAM, continuous latent action models that enable robots to learn from unlabeled demonstrations such as videos. By using continuous latent action labels and jointly training an action decoder, their approach reduces the cost and effort required to train robots for new tasks. Kobayashi proposes CubeDagger, a method to improve the robustness of interactive imitation learning while preserving dynamic stability. This approach transforms the expert-agent switching system to an optimal consensus system and introduces autoregressive colored noise for consistent stochastic exploration. We also see applications in agricultural robotics, with Thea Nenthan and colleagues presenting CottonSim, a simulation-based robotic cotton picking system, and Kwang and colleagues proposing CPP-DIP, a multi-objective coverage path planning framework for micro-air vehicles in irregular plantations. The common thread across these papers is a focus on reducing data collection costs and human supervision requirements, making robot learning more scalable and accessible. Researchers are developing increasingly sophisticated methods to extract maximum value from available demonstration data, whether labeled or unlabeled. The fourth research theme encompasses advanced control and planning techniques, particularly model predictive control and vision-based navigation. Kojima and colleagues propose vehicle motion planning methods with obstacle avoidance in tight spaces by incorporating polygonal approximations into a model predictive control framework. Their approach reformulates disjunctive constraints as tractable conjunctive constraints, making the optimization problem more solvable. Langman and colleagues present an online velocity planner for autonomous racing that adapts to changing dynamic constraints, combining a forward-backward solver with a novel spatial sampling strategy. In the domain of aerial robotics, Sartori and colleagues focus on enabling safe autonomous flight of nano-drones weighing just 30 grams in partially known environments. Their AI-aided, vision-based reactive planning method pushes the boundaries of what's possible with severely resource-constrained platforms. Song and colleagues introduce a simulation-based dataset capturing major structural changes, such as building construction and demolition, addressing the challenge of place recognition in environments that change significantly over time. Across these papers, researchers are finding innovative ways to balance computational constraints with the need for real-time performance in complex dynamic environments. Analyzing these papers reveals several breakthrough results and common themes that highlight the current state of robotics research. First, Liu and colleagues demonstrate that compact models can match or even exceed the performance of larger ones through careful distillation techniques. This finding is particularly significant for deploying sophisticated AI in resource-constrained robotic platforms. Li and colleagues show that exploiting structural symmetry as an inductive bias in policy learning dramatically improves sample efficiency, robustness, and generalization across diverse manipulation tasks. Their approach successfully scales to four-arm manipulation, demonstrating broader applicability beyond typical bimanual setups. Liang and colleagues achieve a remarkable 2 to 3 times improvement in task success rates compared to state-of-the-art baselines by enabling learning from unlabeled demonstrations. This breakthrough significantly reduces the cost and effort required to train robots for new tasks. Sartori and colleagues demonstrate that even severely resource-constrained platforms like 30-gram nano-drones can achieve autonomous navigation using a combination of onboard and edge computing, a significant step for deploying tiny robots in applications like search and rescue. Finally, Sermon and colleagues show that runtime adaptation to user preferences enhances the acceptance of autonomous systems, addressing one of the major challenges in the adoption of autonomous vehicles. Across these papers, several methodological approaches emerge as particularly important for advancing robotics research. Reinforcement learning appears frequently, with researchers developing innovative ways to improve sample efficiency by leveraging structural biases such as morphological symmetry. This approach allows robots to learn complex behaviors through trial and error while requiring less training data. Large language models and vision language models are increasingly being applied to robotics, with researchers developing distillation techniques to maintain reasoning capabilities while reducing computational requirements. These models enable robots to understand and reason about their environment at a semantic level. Model predictive control remains a powerful approach for robotics, allowing systems to handle constraints and optimize actions over a prediction horizon. Researchers are developing more efficient optimization algorithms and combining MPC with learning-based approaches. Imitation learning and learning from demonstration appear in multiple papers, with a focus on reducing dependence on labeled data and expert demonstrations. Techniques such as learning from unlabeled observations and synthetic data augmentation address the data scarcity problem. Finally, simulation continues to play a crucial role in robotics research, with researchers developing increasingly sophisticated methods to bridge the sim-to-real gap through domain randomization and synthetic data generation. Let's examine our first selected paper in greater depth, DSDrive by Liu and colleagues. This research addresses a fundamental challenge in autonomous driving, creating systems that can reason sophisticatedly while remaining computationally efficient enough for real-world deployment. Large vision language models have demonstrated impressive reasoning capabilities, but are too resource-intensive for direct use in vehicles. The authors introduce DSDrive, which employs a distillation approach to transfer reasoning capabilities from larger vision language models to a more compact language model. At the core of their system is a waypoint-driven dual-head coordination module that effectively aligns reasoning and planning tasks, rather than treating these as separate processes. DSDrive integrates them into a unified framework where the planning component anchors on trajectory results while incorporating detailed reasoning insights. Evaluation results show that DSDrive performs on par with or better than benchmark models, despite its more compact size. The computational efficiency is significantly improved, with reduced time and memory requirements during inference. By integrating reasoning and planning, the system provides more interpretable decision-making, explaining both the reasoning behind actions and the planned trajectory. This research represents a significant step toward practical end-to-end autonomous driving systems that can be deployed in real-world vehicles, bridging the gap between sophisticated AI capabilities and the computational constraints of automotive platforms. Our second selected paper, CLAM by Liang and colleagues, addresses a critical challenge in imitation learning for robotics: the high cost of collecting action-labeled demonstrations. Traditional approaches require not only observations, but also corresponding action labels, making data collection time-consuming and expensive. CLAM introduces continuous latent action models that enable learning from unlabeled observations, such as video demonstrations, without requiring action labels. Unlike previous approaches using discrete representations, CLAM employs continuous latent action labels, which the authors found necessary for complex continuous control tasks. The system jointly trains an action decoder to ensure the latent action space can be grounded to real actions with relatively few labeled examples. CLAM operates in two phases. First, it learns a latent action space from unlabeled observations using a sequence model to predict future states. Second, it maps from this latent space to real actions using a small number of labeled examples, which can come from non-expert play data rather than expert demonstrations. Evaluation results show CLAM achieves a 2 to 3x improvement in task success rate compared to baseline methods across multiple tasks. It successfully learns performant policies without any action-labeled expert data and transfers effectively from simulation to real robots. By enabling learning from unlabeled observations and non-expert data, CLAM dramatically reduces the data collection bottleneck in robot learning, potentially making robot training more accessible and scalable. Our third selected paper, SYMDEX by Lee and colleagues, tackles the challenging problem of bimanual manipulation, where robots use two arms to perform tasks that would be difficult or impossible with a single arm. Bimanual manipulation is particularly challenging due to the high dimensionality of the action space and the need for tight coordination between arms. While humans naturally exhibit bilateral symmetry in their manipulation skills, current robotic systems struggle to exploit this property effectively. SYMDEX, symmetric dexterity, is a reinforcement learning framework that leverages the robot's inherent bilateral symmetry as an inductive bias. The system decomposes complex bimanual tasks into per-hand subtasks and trains dedicated policies for each, making the learning problem more tractable by reducing dimensionality. SYMDEX exploits bilateral symmetry via equivalent neural networks, ensuring that experience from one arm is inherently leveraged by the opposite arm. After training the per-hand policies, the system distills them into a global ambidextrous policy that is independent of the hand task assignment. Evaluation results show SYMDEX significantly outperforms baselines on complex tasks where hands perform different roles. By exploiting bilateral symmetry, it achieves greater sample efficiency than baseline approaches. The approach successfully transfers to real-world tasks and scales to a four-arm manipulation setup, demonstrating broader applicability. This research highlights the value of exploiting morphological structure as an inductive bias in policy learning, an approach that could extend to other types of symmetries and structures in robot design. Looking toward the future, several promising research directions emerge from these papers. First, we can expect deeper integration of AI with robotics, with researchers developing robot-specific language and vision models that better connect symbolic reasoning with physical action. These specialized models will likely be more computationally efficient and better grounded in the physical constraints of robotic systems. Second, improved sample efficiency remains a critical goal, with researchers developing techniques to learn from fewer examples while achieving better generalization to new situations. Approaches that leverage structural biases, such as symmetry, and combine multiple learning paradigms show particular promise. Third, advanced manipulation continues to be a frontier area, with researchers working to close the significant dexterity gap between robots and humans. Future work will likely focus on more sophisticated tactile sensing, better integration of vision and touch, and learning approaches that scale to more complex manipulation tasks. Fourth, human-robot interaction will receive increased attention, with systems that can adapt to individual preferences and provide more natural interfaces. As robots move into more human-centric environments, their ability to understand and respond appropriately to human intentions becomes increasingly important. Finally, ethical considerations around robotics will gain prominence, including addressing societal impacts, ensuring safety in human-robot interactions, and developing appropriate regulatory frameworks as these technologies become more widespread. This AI frontier synthesis was created using the Anthropic Claude 3.7 Sonnet model, released in February 2025. The audio you're hearing was generated using OpenAI's text-to-speech technology, which converts the synthesized text into natural-sounding narration. Visual elements accompanying this podcast were created using Stable Diffusion image generation techniques, which produce relevant illustrations based on the content discussed. While automated tools were used to generate this synthesis, the content underwent review by human experts to ensure accuracy, coherence, and appropriate technical depth. Despite thorough review processes, some oversights may exist in the final product. All references to original research papers are provided in the episode description, allowing listeners to explore the primary sources directly. This transparent approach combines the efficiency of AI synthesis with the critical oversight of human expertise to deliver high-quality research communication. To stay updated with the latest developments in robotics and other AI domains, subscribe to AI Frontiers for weekly research syntheses. Our channel brings you comprehensive overviews of cutting-edge research across artificial intelligence, machine learning, computer vision, natural language processing, and more. Join our growing community of researchers, practitioners, and technology enthusiasts to participate in discussions about emerging technologies and their implications. Visit our website to access additional resources, including full paper references, code repositories, and supplementary materials related to the research we cover. We value your feedback and research interests. Share them with us to help shape future episodes and ensure we're covering the topics most relevant to you. Follow us on social media platforms for research highlights, announcements about upcoming episodes, and opportunities to engage with fellow AI enthusiasts. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from archive. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.